Tonight, we are going to look at one experiment, just one. An experiment so simple you could explain the setup to a child in 30 seconds. A wall with two slits in it. A particle gun on one side. A detector screen on the other. That is it. That is the whole apparatus. And what happens when you run this experiment is so deeply fundamentally disturbing that Richard Feynman, one of the greatest physicists of the 20th century, said it contains the only mystery of quantum mechanics, that everything strange and counterintuitive about the quantum world, everything that makes physicists lose sleep and philosophers reach for their pens, is already present in full in this one simple experiment. He was not exaggerating. By the time we are done tonight, you are going to understand exactly what the double-slit experiment shows, not the vague, hand-wavy version you may have heard before, the real version, the precise, careful, experimentally confirmed version. And you are going to feel, in a way that I hope stays with you long after tonight, why physicists describe this result as the most disturbing thing science has ever discovered about the nature of reality. Let us begin. Let us start with what you expect to happen, because the experiment's power comes from the gap between what you expect and what actually occurs. And to feel that gap properly, you need to first build up the expectation. Imagine a wall standing in the middle of a room. In the wall, there are two narrow slits, side by side, close together. On the left side of the wall, you have a gun that fires tiny balls. Metal pellets, small enough to fit through either slit but not both at once. You aim the gun roughly at the two slits and fire pellets, one at a time, at random angles. On the right side of the wall, opposite the slits, there is a screen that records where each pellet lands. What do you expect to see on the screen? You expect two piles, two clusters of hits, one behind each slit, because each pellet, coming from the left, either goes through the left slit or the right slit. Pellets that go through the left slit land on the screen, roughly behind the left slit. Pellets that go through the right slit land roughly behind the right slit. Two piles. Simple, sensible, classical. This is exactly what you get when you run the experiment with actual metal pellets. Now, change the setup. Instead of pellets, use waves. Water waves, for instance. You have a water tank with a barrier across the middle, and in the barrier, two narrow slits. You disturb the water on one side, creating ripples. The ripples travel toward the barrier. What happens when a wave reaches the two slits? The wave passes through both slits simultaneously. On the other side of the barrier, two new circular waves spread out from each slit. These two waves then overlap and interfere with each other. Where the peaks of one wave meet the peaks of the other, they add together, creating a bigger wave. Where the peaks of one wave meet the troughs of the other, they cancel each other out, creating stillness. The result is an interference pattern. On the detector screen, you do not see two piles. You see a series of alternating bands, bright bands where the waves reinforced each other, and dark bands where they canceled. Many bands spread across the screen, a completely different pattern from what particles produce. Interference is the signature of waves. It is what waves do when they overlap, and it is completely different from what particles do. This is the classical picture. Particles make two piles. Waves make an interference pattern. The two behaviors are completely distinct. You can tell, just by looking at the pattern on the screen, whether you are dealing with particles or waves. Now here is where the experiment becomes deeply strange. In the early 20th century, physicists discovered that light, which everyone knew was a wave, also came in discrete packets called photons. Einstein showed this in 1905, explaining the photoelectric effect. Light was granular. It came in chunks, photons. But photons are also waves. The interference experiments that had established the wave nature of light in the 19th century were real. Light really did produce interference patterns, so light was both a wave and a particle, somehow, depending on how you looked at it. And then physicists discovered that electrons, which everyone knew were particles, also produced interference patterns when fired at a double slit. In 1927, Clinton Davison and Lester Germer demonstrated that electrons diffracting off a crystal lattice produced interference patterns. Electrons, solid, definite, point-like particles, producing the interference pattern of waves. Let me make sure you feel exactly how strange this is. You set up the double slit apparatus. Instead of light or water waves, you use an electron gun. You fire electrons, one at a time, at the double-slit barrier. The electrons arrive at the screen one by one. Each electron makes a single dot on the screen. One dot, one electron, a particle hitting a screen. That is all. You fire the first electron, it makes a dot somewhere on the screen. You fire the second electron, another dot somewhere else. Third, fourth, fifth, random seeming dots scattered across the screen. After 100 electrons, the dots still look random. There is no clear pattern yet. But wait, after 1,000 electrons, something starts to emerge. The dots are not evenly distributed. They are clustering in some places and absent from others. After 10,000 electrons, the pattern is unmistakable. The dots have arranged themselves into bands, multiple bright bands separated by dark gaps, an interference pattern. But this is impossible. Each electron was fired separately. Each electron made a single dot. There was never more than one electron in the apparatus at a time. There was nothing for each electron to interfere with. And yet, the cumulative pattern of thousands of individual electron hits is an interference pattern. The pattern that can only be produced by waves overlapping and canceling. Each individual electron, it seems, went through both slits at once. It behaved as a wave, spread across the entire barrier, passed through both openings simultaneously, interfered with itself on the other side, and then landed as a dot at a position determined by that interference. The interference was not between different electrons. It was between the single electron and itself. This alone is extraordinary, but it gets worse, much worse. A skeptic might say, fine, maybe the electron really does go through both slits as some kind of spread-out wave, but can we check? Can we look to see which slit it actually went through? Of course. You place a detector next to each slit. When an electron passes through a slit, the detector fires and tells you which slit the electron went through. You can now track each individual electron and know, for certain, which path it took. You run the experiment again, this time with the detectors in place. You fire thousands of electrons. Each time, one of the detectors fires. You can see that each electron went through one slit or the other. Never both, never neither. One specific slit each time. And you look at the pattern on the screen. The interference pattern is gone. In its place, you see two piles, two clusters of dots, one behind each slit. Exactly what you would expect from classical particles choosing one path or the other. The moment you observe which slit the electron goes through, it stops producing an interference pattern. It starts behaving like a classical particle. And the moment you remove the detectors, the interference pattern comes back. The electron's behavior changes depending on whether it is being observed. Let me say that again very carefully. The electron's physical behavior, where it actually lands on the screen, is different depending on whether there is a detector watching it. Not different in some subtle statistical way, completely different. A fundamentally different spatial pattern. When watched, it acts like a particle and makes two piles. When not watched, it acts like a wave and makes an interference pattern. The act of observation changes the outcome of the experiment. This is the result. This is what has been confirmed thousands of times in laboratories around the world, with electrons, with photons, with neutrons, with entire atoms, with molecules containing 60 carbon atoms, with molecules containing hundreds of atoms. The interference pattern appears when there is no measurement of which path the particle took. The interference pattern disappears when a measurement is made, regardless of how that measurement is made, regardless of how subtle or gentle the measurement is. Observation changes reality. Now you understand why Feynman called this the only mystery. Everything bizarre about quantum mechanics is here. Everything that makes the quantum world so hard to accept, so resistant to common sense, so deeply unlike the world of everyday experience, it all lives in this result. Let us now go back to the beginning and trace this story properly, because the double-slit experiment did not start with quantum mechanics. It started more than 200 years ago with a question about light. Thomas Young was a British polymath of the early 19th century. He was a physician, a linguist, a physicist. He helped decipher Egyptian hieroglyphics. He made fundamental contributions to the understanding of color vision. And in 1801, he performed the experiment that established the wave nature of light, changing the course of physics. At the time, there was a fierce debate about what light was. Isaac Newton, the greatest scientific authority of the age, had argued that light was a stream of particles. His corpuscular theory explained reflection, refraction, and the straight-line travel of light in terms of particles bouncing and bending. Newton's reputation was so immense that his view had dominated for over a century. But Young was not convinced. He thought light was a wave, and he designed an experiment to demonstrate it. He took a single light source and passed it through a small hole to create a coherent beam. Then he passed that beam through a card with two small slits very close together. On the other side, he held a screen. If Newton was right and light was particles, Young expected to see two bright bands on the screen, one behind each slit. What he actually saw was a pattern of alternating bright and dark bands, many bands spread across the screen, an interference pattern. Young recognized immediately what this meant. Only waves could produce this pattern. The two beams of light emerging from the two slits were interfering with each other, just like water ripples overlapping in a pond. Where the peaks aligned, the light was bright. Where peak met trough, the light canceled to darkness. Light was a wave. Young published his results in 1804. The response from the scientific establishment was hostile. The idea of contradicting Newton was almost heretical. One critic attacked Young's work savagely, calling it a feeble attempt to attack the established theory. Young defended his work vigorously, and eventually, as more experiments confirmed the wave nature of light, the corpuscular theory collapsed. By the middle of the 19th century, light was universally accepted as a wave. Then came Maxwell. James Clerk. Maxwell unified electricity and magnetism in the 1860s and showed that light was an electromagnetic wave, a self-propagating oscillation of electric and magnetic fields traveling through space. The wave nature of light was not just confirmed, it was explained, it was derived from deeper laws of physics. The 19th century ended with physics in a triumphant state. Classical mechanics described the behavior of matter with extraordinary precision. Thermodynamics explained heat and energy. Electromagnetic theory explained light and electricity. The universe seemed to be a great machine, running according to fixed knowable laws. The job of physics seemed almost complete. Then the 20th century began, and everything fell apart. The first crack appeared with a seemingly minor puzzle about light emitted by hot objects. Theoretical calculations based on classical physics predicted that a hot object should emit infinite energy at short wavelengths, which was obviously absurd. No one could make the theory agree with the experimental measurements of how hot objects actually radiate. In 1900, Max Planck found a mathematical trick that fixed the calculation. He assumed that light was emitted not continuously, but in discrete chunks, each with an energy proportional to the frequency of the light. He called these chunks quanta. The mathematics worked perfectly. Planck was not sure whether the quanta were real or just a mathematical device, but the equations fit the data and the problem was solved. Then Einstein, in 1905, took Planck's idea seriously and extended it. If light is emitted in discrete quanta, he argued, perhaps it also travels as discrete quanta. Perhaps light is, in some sense, made of particles after all. He used this idea to explain the photoelectric effect, the observation that light striking a metal surface could eject electrons, but only if the light was above a certain frequency, regardless of its intensity. This made no sense for waves, but made perfect sense for particles, or quanta of light, which were later named photons. Einstein's photoelectric explanation won him the Nobel Prize, but it created a terrible problem. Young's double-slit experiment had conclusively shown that light was a wave. Maxwell's equations had explained that wave in terms of oscillating electromagnetic fields, and now Einstein was saying light was particles. Which was it? The answer, as quantum mechanics would eventually reveal, is both, and neither. Light is something for which the human concepts of wave and particle are both inadequate, both partially right, both ultimately wrong. Light is a quantum object. It behaves like a wave in some experimental contexts and like a particle in others. The behavior depends on how you look at it. This wave-particle duality, as it came to be called, was the first sign of how deeply the quantum world differed from the classical world. In classical physics, something is either a wave or a particle. These are mutually exclusive categories. You cannot have something that is both, depending on circumstances. but quantum objects are both, depending on circumstances, and the double slit experiment makes this duality visible in the starkest, most unavoidable way. After physicists accepted that light had particle properties, the question naturally arose, do particles have wave properties? Could electrons, which were obviously point-like particles carrying definite charge and mass, also exhibit wave behavior? Louis de Broglie, a French physicist, proposed in 1924 that every particle has an associated wavelength, given by a simple formula relating wavelength to the particle's momentum. The faster and heavier the particle, the shorter its wavelength. For everyday objects, the de Broglie wavelength is absurdly small, far too small to produce any measurable wave effects. But for electrons, the wavelength was measurable, and if electrons had wavelengths, they should produce interference and diffraction patterns. This was a radical prediction. Electrons were understood to be particles. The idea that they had wavelengths seemed almost metaphorical. Then Davison and Germer, working at Bell Labs in New York, accidentally confirmed it. They were studying how electrons reflected off a nickel crystal. During an experiment, the crystal was accidentally heated, which changed its structure, and when they resumed their measurements, they found that the electrons were reflecting in unexpected ways. Analyzing the data, they realized that the electrons were diffracting off the crystal lattice like X-rays, like waves. The pattern of reflection matched perfectly with de Broglie's predicted wavelength. Electrons had wave properties. The double slit experiment, applied to electrons, was not a thought experiment. It was a prediction of reality, and reality confirmed it. Now, let us come back to the central mystery. Because I want to make sure we have examined it from every angle, because the experiment has been refined and extended in ways that make the strangeness even harder to escape. The key question is always the same. Can we figure out which slit the particle went through without disturbing its behavior? Physicists have been extraordinarily creative in trying to answer this question. They have designed experiments with ever more subtle, ever more minimally invasive ways of detecting which path the particle takes. And the answer is always the same. Any experiment that succeeds in determining which slit the particle went through destroys the interference pattern. Any experiment that preserves the interference pattern fails to determine which slit the particle went through. The two things are mutually exclusive. You cannot have both. You can know the path, or you can see the interference. Not both. This is not a practical limitation. It is not that our detectors are too clumsy or our technology insufficiently advanced. It is a fundamental feature of quantum mechanics. Knowing the path and seeing the interference are incompatible. The universe does not allow both simultaneously. Werner Heisenberg formulated this as his uncertainty principle in 1927. The more precisely you know a particle's position, including which slit it went through, the less precisely you know its momentum, including the direction it is traveling after the slit. And it is precisely the spread in momentum, the spread in the direction of travel, that creates the interference pattern. Pinning down the path kills the spread in momentum and kills the interference. The uncertainty principle is not a statement about our ignorance. It is a statement about what the universe permits to be simultaneously definite. But let us go further, because there is a version of the experiment that is even more disturbing than the basic which-way detector version. It is called the delayed choice experiment, and it was proposed by John Wheeler in 1978. Wheeler asked, what if you wait until after the particle has passed through the slits before deciding whether to observe which path it took? Here is the setup. The double slit experiment is running. Particles are being fired one at a time. Each particle passes through the slits and travels toward the detector screen. But the detector screen is far away, far enough that there is a significant delay between when the particle passes through the slit and when it arrives at the screen. While the particle is in flight, after it has already gone through the slit or slits, you flip a switch. You decide, at that moment, whether to measure which path the particle took or to let it arrive at the screen undisturbed. If you decide to measure the path, placing a which-way detector in the apparatus, you find that the particle went through one specific slit. And when you look at the accumulated pattern over many shots, there is no interference. If you decide not to measure the path, letting the particle arrive freely, you get an interference pattern. But you made this decision after the particle had already passed through the slits. How did the particle know, when it was at the slits, what you were going to decide later? How could the particle have acted like a wave passing through both slits if the decision to measure came after it had already passed through? This thought experiment was actually performed. In 1984, Carol Alley and colleagues performed an experimental version with photons. The results matched quantum mechanics perfectly. The pattern depended on whether a which-way measurement was made, even when that decision came after the photon had already passed through the slits. In 2007, a French team led by Alain Aspect performed an even more refined delayed choice experiment. The decision of whether to measure the path was made by a quantum random number generator after the photon was already in flight. The results were again perfectly consistent with quantum mechanics. The interference pattern appeared when no measurement was made, regardless of when the decision not to measure was made. And it disappeared when a measurement was made, regardless of when the decision to measure was made. What does this mean? One interpretation is that the particle somehow knows what is going to happen in the future. That the future measurement reaches back and influences the past behavior of the particle. That causality runs backward. This sounds insane. And in a certain sense, it is. But quantum mechanics provides another way to think about it that is slightly less insane, though not much more comfortable. The quantum mechanical description says that there is no definite reality for the particle between preparation and measurement. The particle does not have a definite path. It does not go through the left slit or the right slit. It exists in a superposition of going through both. This superposition is not a statement about our ignorance. It is a statement about what actually is. The particle genuinely has no definite path until a path is measured. When you measure the path, you bring a definite path into existence. When you do not measure the path, you bring an interference pattern into existence. When you measure the path is not the important question. What matters is whether a path is measured at all before the particle reaches the final detector. In the delayed choice experiment, the decision to measure or not measure is made after the particle has passed the slits, but before it reaches the final detector. And that is what matters. The question of what the particle did at the slits does not have a definite answer until the entire experiment is complete. Until then, both possibilities exist simultaneously. This is deeply uncomfortable. It seems to say that the past is not fixed, that what actually happened at the slits depends on what you decide to do later. That history is written retroactively at the moment of measurement. John Wheeler, who proposed the delayed choice experiment, embraced this conclusion in a dramatic way. He proposed that observation is not just passively revealing a pre-existing reality. Observation participates in creating reality. He called this the participatory universe. The idea that the universe at the quantum level does not have a definite existence independent of the observations that are made of it. That reality is, in some sense, brought into being by the act of looking. This is not mysticism. Wheeler was a rigorous physicist, one of the great theoretical physicists of the 20th century, the man who coined the term black hole. He was saying something precise and testable, and the tests have confirmed it. The universe behaves as if reality does not fully exist before measurement. Now, I want to address something that comes up almost every time someone learns about the double slit experiment. The obvious question: what counts as an observation? Does it have to be a human observer? Does it have to be a conscious mind? Could a camera count? A rock? This question gets to the heart of the measurement problem, which we discussed in our exploration of quantum entanglement. And the answer is both clearer and more troubling than most people expect. It does not have to be a conscious observer. A camera counts. A rock does not, in the relevant sense. What matters is not consciousness. What matters is whether the information about which path the particle took has become encoded in the environment in an irreversible macroscopic way. When a detector fires because an electron passes through it, the firing of the detector is a macroscopic, irreversible event. A large number of atoms in the detector have changed state. The information about which slit the electron went through has been amplified from the quantum to the classical level. It has become, in principle, readable. That is what destroys the interference pattern. When an electron passes through a slit with no detector, nothing macroscopic changes. No irreversible record is made. The information about which slit the electron went through does not become encoded in the environment, and so the interference pattern survives. This is the process of decoherence that we have discussed. The detector, by becoming entangled with the electron, spreads the information about the electron's path into the environment. Once that spread has happened, the different paths are correlated with different orthogonal states of the environment. They can no longer interfere. The interference pattern is gone. Consciousness is not required, but measurement, in the technical quantum mechanical sense, the irreversible amplification of quantum information into a macroscopic record, is required, and once it has happened, the interference is gone. This might seem like a relief. Maybe the universe is not actually observer-dependent in a spooky, consciousness-dependent way. Maybe it is just about irreversible records and decoherence. Maybe we can keep a picture of reality as something that exists independently of minds, as long as we are careful about what we mean by observation. But this relief is not quite as secure as it might seem, because decoherence explains why the interference pattern disappears when a which-way measurement is made. It does not explain what actually happens to the particle. It does not tell you which slit the electron actually went through. It does not give you a definite, classical story of what physically occurred. What decoherence tells you is that different branches of the quantum superposition stop being able to interfere with each other once they become entangled with different states of the environment. The superposition does not collapse, it spreads. The electron in the left slit is now correlated with the detector having fired on the left. The electron in the right slit is now correlated with the detector having fired on the right. These two branches of the superposition can no longer interfere. They are, in practical terms, separate. But both branches still exist in the full quantum state of the universe. Quantum mechanics, applied consistently, says they are both real. The electron went through the left slit in one branch and the right slit in another branch. Both happened. You only experience one because you are now entangled with the detector, and your experience is in one branch. This is the many worlds view, and in the many worlds view, the double slit experiment has a simple explanation. Every time the electron passes through the slits, the universe splits. In branches where no which-way measurement is made, the two branches of the superposition can still interfere, and the interference pattern emerges. In branches where a which-way measurement is made, the two branches become correlated with different detector states and can no longer interfere, and the two-pile pattern emerges. But you, as an observer in one branch, always see one or the other, never both. The many worlds view is clean and elegant. It avoids the collapse of the wave function. It is consistent with the Schrödinger equation applied to everything without exception. But it comes with a price, an infinite proliferation of branches, of parallel realities, of versions of you that made different decisions and saw different results. And the question of what it means for something to be probable when all outcomes occur remains deeply problematic. The Copenhagen view, the traditional interpretation, says something different. It says, do not ask what is happening between measurements. The wave function is a calculational tool. It gives you the probability of each outcome when a measurement is made. When a measurement is made, the wave function collapses. The particle acquires a definite state. Where it acquires that state, what physically happens during collapse is not a question Copenhagen answers. The theory is complete as a predictive framework, and asking for more is asking for something beyond what physics can or should provide. Many physicists find Copenhagen deeply unsatisfying. It builds the measurement, a macroscopic classical act, into the foundations of a theory that is supposed to describe the microscopic world. It draws a sharp line between quantum and classical without saying where that line is or why it exists. And it refuses to say what is really happening, which seems to abandon one of the core goals of science. Other interpretations exist. Pilot wave theory, which we have discussed. Relational quantum mechanics, which says that quantum states are always relative to an observer, and there is no observer-independent reality. QBism, or quantum Bayesianism, which says that the wave function represents an agent's beliefs about the outcomes of measurements, not an objective feature of the world. These and others are all attempts to make sense of what quantum mechanics is telling us about reality. None of them is universally accepted. And none of them fully resolves the unease that the double-slit experiment creates. All of them are grappling with the same central fact. The act of measurement changes the outcome. Let me now tell you about some of the more recent versions of the double-slit experiment because they push the strangeness even further than the basic electron version. In 1999, a team at the University of Vienna, led by Anton Zeilinger, performed the double-slit experiment with molecules of Buckminster fullerene, or C60. These are soccer ball-shaped molecules made of 60 carbon atoms, large enough to see with a decent microscope. With a diameter of about 1 nanometer, they fired these molecules through a diffraction grating, the optical equivalent of a double slit, and observed an interference pattern, 60 atom molecules behaving like waves, passing through both slits simultaneously, interfering with themselves. The wave-particle duality does not stop at electrons or photons. It extends to increasingly large and complex objects. In 2019, the same group reported interference experiments with molecules containing nearly 2,000 atoms, with masses over 25,000 atomic mass units. These are molecules so large and complex that they stagger the imagination when you think of them as waves, and yet they produce interference patterns. They go through both slits at once. How far does this go? Is there a limit? At what scale does quantum behavior give way to classical behavior? This is one of the most important open questions in physics. Theoretically, the Schrödinger equation applies to everything, at all scales. There is no built-in limit. Any object, in principle, can be in a superposition, can exhibit wave behavior, can produce an interference pattern. But in practice, as objects get larger, decoherence happens faster and faster. The interference pattern becomes harder and harder to see because the object is constantly interacting with its environment, constantly entangling, constantly leaking information about its state into the surroundings. For a baseball, the decoherence happens so fast that the baseball is effectively classical from the moment it is created. You will never see a baseball produce an interference pattern, not because quantum mechanics does not apply to it, but because the baseball is so thoroughly entangled with its environment that its quantum coherence is destroyed before any wave effects can be observed. But the transition from quantum to classical is not sharp, it is gradual, and as experimental techniques improve, researchers are pushing the quantum classical boundary to larger and larger objects. They are working toward interference experiments with viruses, with small proteins, with eventually micron-scale objects that are near the edge of what can be seen with the naked eye. Each step pushes the boundary and tests how far the quantum world extends. There is also a version of the delayed choice experiment that has been extended in an even more mind-bending direction. It is called the quantum eraser experiment, and it involves not just deciding whether to measure the path, but erasing the measurement after it has been made. Here is the idea. You perform the double slit experiment and you do measure which path the photon took. The interference pattern disappears. You have path information. Now, before the photon reaches the detector screen, you take the path information and destroy it. You erase it. You take the particle that carried the which-way information and perform a measurement on it that makes it impossible to recover which path the original photon took. When you erase the which-way information, the interference pattern comes back. The photon's behavior at the screen, whether it makes an interference pattern or two piles, depends on whether the which-way information is available anywhere in the universe at the moment it arrives. If the information is available, even if you are not looking at it, no interference. If the information is erased, even if it was available a moment ago, interference returns. The quantum eraser was first proposed by Marlon Scully and Kai Watkevich in 1982 and experimentally demonstrated in 1995. It is perhaps the most striking demonstration of the principle that the behavior of a quantum particle is not determined by what happens to it at a specific moment, but by the entire experimental context, including what information about its history is available anywhere in the universe. The universe is keeping track, not of the particle's position, of whether information about the particle's position is available, and it adjusts the particle's behavior accordingly. This is what the double slit experiment has been teaching us in ever deeper ways for more than 2 centuries. Reality at the quantum level is not about objects with definite properties moving along definite paths. It is about information, about what is knowable, about what distinctions the universe is maintaining. When a which-way distinction exists somewhere, the interference disappears. When no which-way distinction exists anywhere, the interference appears. The universe behaves as if it knows what you know, as if the available information shapes the physical outcomes, as if knowledge and reality are not as separate as we assumed. This is the mystery at the heart of the double-slit experiment. Not just that particles act like waves when unobserved, but that the universe seems to be, in some deep sense, informational. That what physically happens depends on what information is available. That reality is not a fixed, observer-independent structure that we passively observe, but something that is, at the quantum level, shaped by observation. John Wheeler again put it this way. He said, "No phenomenon is a phenomenon until it is an observed phenomenon. Nothing is real until it is measured. The act of observation is not the passive recording of a pre-existing fact. It is the participatory creation of fact." This is a statement that physicists argue about endlessly. Some accept it, some reject it, some say it is too philosophical to count as physics. But all of them have to contend with the experimental results. And the experimental results say that the double-slit experiment, in all its forms, produces outcomes that depend on what information is available about the particle's path. Interpretation can be disputed, the results cannot. Let me now bring this back to something immediate, something that connects the abstract quantum mystery to your experience of being alive. You have been an observer your entire life. Every time you have looked at something, opened your eyes in the morning, glanced at a friend's face, read a line of text, you have been performing the quantum act of observation, not in a mystical sense, in a physical sense. Photons have bounced off objects and entered your eyes, triggering chemical reactions in your retina, sending electrical signals to your brain. Information has flowed from the world into you, and at the quantum level, that act of information flow has had physical consequences. The photons bouncing off the objects became entangled with your visual system. Their quantum states were measured, their superpositions collapsed. Definite outcomes emerged. You have been collapsing wave functions your entire life, not consciously, not through any special power of mind, but through the simple physical act of being a macroscopic system that interacts with the world and records information about it. In a universe without observers, a universe with no macroscopic systems that record information, no detectors, no cameras, no eyes, everything would remain in superposition. There would be no definite facts. There would only be potentialities. The double-slit experiment with no screen and no detector would produce no pattern. There would be nothing to produce a pattern on. It is the existence of large, complex information recording systems like you that makes definite facts exist at all at the quantum level, not because consciousness is magical, but because irreversible macroscopic records are what turn quantum potentialities into classical actualities. You are not just a passive observer of the universe. You are part of the mechanism by which the universe becomes definite, by which probabilities become facts, by which the quantum world crystallizes into the classical world you experience. This is a remarkable thing to sit with. The world you see around you, solid, definite, full of objects with specific properties in specific locations, is not a given. It is a product of the interaction between the quantum world and the macroscopic systems, including you, that observe and record it. The definiteness of the world is not built into the fundamental physics. It emerges from observation. And the double-slit experiment is the clearest window into this fact. 2 slits, 1 particle, an interference pattern that appears when no one is watching and vanishes the moment someone looks. The universe, showing its cards, telling you, in the simplest possible setup, that the relationship between observation and reality is nothing like what common sense assumes. Let me close with one final thought. Thomas Young, in 1801, shone light through 2 slits and saw bands of brightness and darkness that he knew, instantly, were the signature of waves. He was using the double-slit experiment to answer a question about the nature of light. He got his answer. Light is a wave. But the experiment did not stop there. It kept giving answers to questions that had not yet been asked. It told us that particles are waves too, that waves are particles, that observation changes outcomes, that which-way information destroys interference, that erasing that information restores it, that the future choice of whether to measure can determine what happened in the past. That reality at the quantum level does not have a definite existence independent of observation. 220 years of physics, extracted from two slits in a wall, Young built a simple apparatus to answer a simple question and accidentally opened a door to the strangest room in science. We have been exploring that room ever since. Every experiment we have done inside it has confirmed how strange it is, how deeply it differs from the world outside it, how fundamentally our common sense assumptions about reality must be revised in its presence. And we still do not fully understand it. The measurement problem is unsolved. The interpretation debate is alive. The question of why observation collapses the wave function, what physically happens during a measurement, where exactly the quantum world ends and the classical world begins. These remain genuinely open. The double slit experiment has been with us for over 2 centuries. It is still teaching us. It is still, in 2025, generating new experiments, new results, new insights. The door Young opened has not yet been fully explored. We are still standing in the room, looking around, finding new strange things in every corner. And the most important thing you can take from tonight is this. The strangeness is not a mistake. It is not a failure of physics. It is not something that will be explained away by a better theory in a more comfortable direction. Every attempt to make the double slit experiment less strange has confirmed how strange it is. Every deeper look has revealed a deeper mystery. The universe, at its most fundamental level, is not the classical common sense world you experience. It is something far stranger, far more interesting, and far less understood. That is not a failure, that is an invitation. Before we truly close tonight, I want to take you into some territory that most explorations of the double slit experiment never reach. Territory that shows you this is not just a curiosity from the early days of quantum mechanics. It is alive. It is still being pushed, and what it is revealing about the nature of reality is getting stranger, not less strange, as the experiments improve. Let us talk about the quantum eraser experiment in more detail, because it is perhaps the single most mind-bending refinement of the double slit, and it deserves more than a paragraph. Here is the setup. You take a standard double slit experiment and you add a pair of entangled photons. Instead of firing single photons directly at the slits, you create pairs of photons using a process called spontaneous parametric down conversion. Each pair consists of 2 photons, a signal photon that goes to the slits, and an idler photon that goes to a different detector entirely. The signal photon goes through the double slit and arrives at a screen. The idler photon goes to a separate detector that you can manipulate. Now, if you do nothing with the idler photon, the signal photon shows an interference pattern on the screen. Good, normal, but here is where it gets strange. Because of the way the photon pairs were created, if you measured the idler photon in a certain way, you could determine which slit the signal photon went through. The 2 photons are entangled, and the path information of the signal photon is encoded in the quantum state of the idler. When you set up the idler detector to measure which path the signal took, the interference pattern for the signal photons disappears. 2 piles instead of interference bands. Even though you have not touched the signal photons at all. Even though the signal photons hit the screen first, before the idler photons reach their detector. The act of what you are about to do with the idler photon, the fact that path information is about to be revealed, affects the pattern the signal photon makes on the screen. Now, for the eraser. You modify the idler detector so that, instead of revealing which path the signal took, it erases that information. You perform a measurement on the idler photon that makes it impossible, even in principle, to determine which path the signal photon took. You have erased the which-way information. When you look at the screen, sorting the signal photon hits by what happened to the corresponding idler, you find that the signal photons whose idlers were measured in the erasing way show an interference pattern. The signal photons whose idlers were measured in the path revealing way show no interference. The same signal photons, hitting the same screen, but depending on what happened to their entangled partners, they contribute to different patterns, and you can only see this by correlating the 2 datasets after the fact. Here is what makes this so deeply disturbing. In some versions of this experiment, the idler photon travels a much longer path than the signal photon. The signal photon hits the screen first. Only later does the idler photon reach its detector, and the decision about whether to erase or reveal is made. The signal photon hits the screen before the idler photon reaches its detector, before the decision is made. And yet, the pattern the signal photon contributes to depends on a decision that has not yet been made. This has been performed experimentally. In 2000, Yoon-Ho Kim and colleagues at the University of Maryland performed the delayed choice quantum eraser experiment. The results were exactly as quantum mechanics predicted. The pattern depended on what happened to the idler photon, even when the signal photon had already hit the screen before the idler measurement was made. Quantum mechanics predicts this correctly, but explaining how the signal photon knew what was going to happen to its entangled partner, when that partner's fate had not yet been decided, requires abandoning any simple picture of reality in which cause precedes effect and particles travel definite paths. The universe is doing something here that has no classical analog. The signal photon, having already landed on the screen, behaves as if it was part of an interference pattern or part of a two-pile pattern, depending on what will happen to its entangled partner in the future. Not based on what has happened, based on what will happen. There are ways to describe this within quantum mechanics without invoking backward causation. The correlation between signal and idler is encoded in their joint quantum state, which is established at the moment the pair is created. The apparent backward causation is a consequence of looking at the signal photons in isolation without considering the full entangled state. When you account for the entanglement properly, there is no contradiction with causality. But the correct description is so unlike anything in classical physics that calling it non-paradoxical is more a matter of convention than genuine resolution. The mathematics works. The experiment confirms the mathematics. The picture of reality that the mathematics implies is one in which the past, the present, and the future are not related in the way common sense assumes. Now I want to tell you about another frontier that the double slit experiment has opened. The question of gravity and quantum mechanics. One of the deepest unsolved problems in all of physics is how to reconcile quantum mechanics with general relativity, Einstein's theory of gravity. Quantum mechanics describes the microscopic world of particles with extraordinary precision. General relativity describes the macroscopic world of space-time with extraordinary precision. But the two theories are fundamentally incompatible. They make different assumptions about the nature of space, time, and causality. When you try to apply both simultaneously in situations where both quantum effects and gravitational effects are important, the equations break down and give infinities. Nobody has yet successfully built a theory of quantum gravity. String theory is a candidate. Loop quantum gravity is another. But neither has been experimentally confirmed, and the fundamental problem of how to combine the two great theories of physics remains open. The double slit experiment has a role to play in this search. In recent years, physicists have proposed experiments that test quantum mechanical principles in the presence of gravity. One proposal, by Marcus Aspelmeyer and colleagues, involves putting a small, massive object into a quantum superposition and observing the gravitational field it produces while in that superposition. Does a quantum superposition of masses create a quantum superposition of gravitational fields? Does gravity respond to quantum states in the same way that quantum mechanics says it must? Answering this would give us a first experimental glimpse into the quantum nature of gravity. More directly relevant to the double slit, physicists have proposed versions of the experiment that test whether gravitational interactions can distinguish which path a massive particle took, even without a conventional detector. The idea is that if gravity is quantum, then a massive particle in a superposition of two paths should produce a quantum superposition of gravitational fields, which cannot be used to determine the particle's path without destroying the interference. But if gravity is classical, the gravitational field might distinguish the paths in a classical way, destroying the interference without the usual quantum measurement. These experiments have not yet been performed. The technical challenges are immense, but they represent one of the most exciting directions in experimental physics, precisely because the double slit experiment sits at the intersection of quantum mechanics and gravity in a way that could reveal something fundamental about the nature of both. There is also the question of consciousness. I want to address this directly because it comes up constantly when people discuss the double slit experiment, and it deserves a careful treatment. Some people, including some physicists, have suggested that the role of the observer in quantum mechanics implies that consciousness is fundamental to physics, that the wave function collapses because of conscious observation, that the universe requires minds to become definite. This view was suggested by some of the founders of quantum mechanics, including John von Neumann and Eugene Wigner in the 1930s. The modern consensus among physicists is that this is not necessary and probably not correct. Decoherence, as we have discussed, explains why macroscopic objects appear to have definite states without invoking consciousness. The relevant threshold is not consciousness, but irreversibility. When quantum information about a particle's path becomes encoded in the environment in an irreversible macroscopic way, the interference disappears. This can happen through any physical process, including one that involves no minds at all. But here is the thing. Decoherence explains why we cannot observe the interference in macroscopic situations. It does not fully explain why we observe definite outcomes rather than superpositions of outcomes. When you measure the spin of an electron and get spin up, decoherence explains why you do not see spin up and spin down simultaneously, but it does not tell you why you got spin up rather than spin down. It does not give you a clear story of what physically happened. The measurement problem, which we have encountered before, lurks here too. Decoherence suppresses the ability of different branches of the wave function to interfere, but in the many worlds view, both branches still exist. The electron goes through the left slit in one branch and the right slit in another. The interference between these branches is suppressed by decoherence, but you, as an observer, are in one branch and not the other. What determines which branch you are in? What makes your experience of the spin-up result real while the other branch is also real? These questions are not answered by decoherence. They are the heart of the measurement problem, and they remain genuinely open. The role of consciousness in quantum mechanics is not settled. The extreme view that consciousness collapses the wave function is rejected by most physicists. The opposite extreme, that consciousness is completely irrelevant to quantum mechanics, is also not quite right, because conscious experiences are the data we are trying to explain. And any account of quantum mechanics must eventually make contact with why observers like us see definite outcomes. The truth is probably somewhere in the middle. Consciousness is not special in a mystical sense, but experience, observation, and information processing are deeply intertwined with the physics of quantum measurement in ways that are not yet fully understood. The double-slit experiment does not resolve this, but it makes the question impossible to ignore, because the result, that observation changes the outcome, that which way information destroys interference, that the quantum eraser can restore it, forces you to think carefully about what observation is, what information is, and how they relate to physical reality. Let me also tell you about something that happened very recently that has extended the double-slit experiment into a completely new domain. In 2022, a group of physicists performed a double-slit experiment with time rather than space. In the traditional double-slit experiment, the two slits are separated in space. The particle passes through two spatially separated holes. In the time domain version, there is only one slit, but it opens at two different moments in time. A short pulse of light hits a material that becomes momentarily transparent, allowing the light to pass through. This happens twice, at two different moments separated by a tiny interval of time. The light pulse, passing through the material at two different moments, interferes with itself in time, producing a pattern in the frequency domain, the equivalent of the interference pattern in space for the regular double slit. This is the temporal double slit experiment. It shows that wave-particle duality and quantum interference are not just spatial phenomena. They operate in time as well. Particles can be in a superposition of passing through a barrier at different times, just as they can be in a superposition of passing through different spatial locations. The temporal double slit is at the frontier of experimental physics. It opens new ways to study quantum coherence and decoherence, and potentially new ways to test the quantum nature of time itself. Because if particles can be in a superposition of different times, what does that say about the nature of time in quantum mechanics? Is time, like space, something that quantum systems can exist in a superposition of? If so, what does that mean for our understanding of causality and the flow of time? These are questions that the temporal double-slit experiment is beginning to probe, and they connect back to the deepest mysteries of quantum mechanics, the ones that the original double-slit experiment first revealed 2 centuries ago. Now, let me bring this all together and close. 2 slits, 1 particle. the most disturbing experiment in the history of science. It started as a question about light. Young was trying to settle the debate between Newton and Huygens. He got his answer. Light is a wave, but the answer opened a door. Behind that door was wave-particle duality. Behind that was the quantum revolution. Behind that was the measurement problem. Behind that was the uncertainty principle, entanglement, decoherence, the delayed choice experiment, the quantum eraser, and now the temporal double slit. Each step deeper has revealed a stranger world. Each explanation has generated a deeper mystery. Each experiment has confirmed not that quantum mechanics is strange, but that reality itself is strange in the precise, measurable, reproducible way that quantum mechanics describes. You cannot perform the double slit experiment and come away with the same picture of reality you had going in. Not if you take it seriously. Not if you follow the logic to where it leads. The logic leads somewhere uncomfortable, to a world in which observation participates in reality, in which information shapes physical outcomes, in which the past is not fully fixed until a measurement has been made, in which particles are neither here nor there until you look. This is the world quantum mechanics describes. It has been tested more carefully and more precisely than any other theory in the history of science. Its predictions are confirmed to more decimal places than any other physical theory. It is, by the standard measures of science, the most successful theory ever devised. And what it is telling us about the nature of reality is that our common sense picture of the world is, at the fundamental level, wrong. Not a little bit wrong, not wrong in some domain, far from everyday experience. Wrong in principle, at the level of the most basic building blocks of matter, in a way that persists and accumulates into the world we experience only because of the overwhelming dominance of decoherence at macroscopic scales. The classical world is real, but it is not the full story. It is the story as seen through the lens of decoherence and measurement, which filters out the quantum strangeness and gives you the familiar, solid, definite world of chairs and tables and coffee cups. Beneath that world is something else. Something that the double slit experiment makes visible, if you are willing to look. Something that does not behave like particles or waves, that is changed by observation, that encodes information about its context in a way that shapes its physical behavior, that does not have a definite past until someone looks. Thomas Young, in his darkened room, with his candle and his card, had no idea what he was opening. He was just trying to settle an argument about light. He settled it. And in doing so, he launched 2 centuries of the most profound, most disturbing, most productive scientific investigation in human history. The experiment is still running. The mystery is still alive. The room is still strange, and tonight, you have looked inside it. But before you sleep, I want to walk you through one more layer of this story, the human layer. Because physics is not done by equations alone. It is done by people. And the people who wrestled most deeply with the double slit experiment left behind some of the most extraordinary intellectual dramas in the history of science. Werner Heisenberg was 23 years old when he began the work that would lead to the uncertainty principle. He was ill with hay fever, had retreated to the island of Helgoland off the German coast to recover. And in that isolated, uncomfortable setting, he worked out the mathematical framework that would become the first formulation of quantum mechanics. He was struck, in those late-night sessions on Helgoland, by a strange feeling of vertigo, as if he were looking down into a deep well and not being able to see the bottom. The uncertainty principle came from his insistence that physics should only talk about things that can be observed. If you cannot observe a particle's position and momentum simultaneously with arbitrary precision, then the theory should not pretend that both have definite values simultaneously. His principle was not a statement about the limits of measurement. It was a statement about the limits of reality. Position and momentum, below a certain scale, are not simultaneously defined, not because we cannot measure them, but because they do not simultaneously exist. Niels Bohr, who was in many ways the philosophical architect of quantum mechanics, engaged in epic intellectual battles with Einstein over the double slit and its implications. These battles are documented in Bohr's recollections, in Einstein's letters, in the memoirs of physicists who witnessed them. Einstein devised thought experiment after thought experiment, trying to find a way to measure the path of a particle through the double slit without disturbing its interference pattern. He would arrive at the Solvay conferences, the great international physics meetings of the 1920s and 1930s, with a new thought experiment. Bohr would spend the night working through it, finding the flaw. By morning, he had refuted it. One famous exchange involved Einstein suggesting that you could measure which slit the particle went through by measuring the recoil of the screen on which the slits were cut. When a particle passes through the left slit, the screen recoils slightly to the right. When it passes through the right slit, it recoils to the left. If you could measure this recoil precisely enough, you could determine which slit the particle used. Bohr's response was to apply the uncertainty principle to the screen itself. If the screen is flexible enough to allow you to measure its recoil, its momentum, with sufficient precision, then its position, including the position of the slits, becomes uncertain. And if the position of the slits is uncertain, the interference pattern is smeared out and disappears. The act of measuring the recoil of the screen to determine which slit the particle used inevitably destroys the interference pattern. The uncertainty principle protects quantum mechanics from Einstein's attack. Einstein was forced to concede, but he was never satisfied. He continued to believe that quantum mechanics was incomplete, that there must be something underneath, something more complete, something that would restore the sense that particles have definite paths and that reality exists independently of observation. The EPR paper of 1935, which we discussed in our exploration of entanglement, was Einstein's last great attempt to show that quantum mechanics must be incomplete. Bohr responded to it in a paper that most physicists found convincing, and that Einstein found unconvincing. They never resolved their disagreement. They held fundamentally different intuitions about what physics was and what the world was. Einstein wanted a physics that described an objective reality, one that existed independently of observers, one in which God does not play dice. Bohr wanted a physics that described what we can observe and measure, one that did not make claims about what reality is like when no one is looking. The double-slit experiment sits exactly at the divide between them. Einstein looks at it and says, the particle must have gone through one slit or the other. The wave function must be an incomplete description of the real physical state. There must be hidden variables that tell the particle what to do. Bohr looks at it and says, the particle does not have a definite path. The question of which slit it went through is not a question with a definite answer unless you measure it. Quantum mechanics is complete. Bell's theorem eventually provided a way to test which of them was closer to right, and the tests found that local hidden variables, the kind Einstein had in mind, cannot reproduce the quantum predictions. Bohr was closer. But the question of what quantum mechanics means, what it is saying about reality, is still not resolved. The debate has changed in character, but it has not ended. Richard Feynman, in his famous Feynman lectures on physics, written in the early 1960s, devoted an entire chapter to the double-slit experiment. He called it the experiment with two holes and said that it has in it the heart of quantum mechanics. He walked through the experiment with electrons with extraordinary care and concluded with a statement that I want you to hear. He said that quantum mechanics describes nature as absurd from the point of view of common sense, and it agrees fully with experiment, so I hope you can accept nature as she is, absurd. Feynman's point was not that quantum mechanics is irrational or that we should give up trying to understand it. His point was that the demand that nature match our intuitions is a demand we have no right to make. The universe is not obligated to make sense to creatures who evolved to navigate a world of rocks and trees and predators. The double-slit experiment shows us what the universe is actually like at the scale of electrons and photons, and at that scale, it is profoundly unlike anything we have experience with. That is not a failure of physics. That is what physics looks like when it is working. Feynman himself, despite spending decades working with quantum mechanics, developing quantum electrodynamics, the most precisely tested theory in all of science, always maintained that nobody really understands quantum mechanics. Not in the sense of feeling intuitively comfortable with it. You can learn to use it. You can learn to make calculations with it. You can learn to predict its outcomes with extraordinary accuracy. But understanding it in the sense of having a clear, intuitive picture of what is actually happening, that, Feynman said, nobody has achieved. Paul Dirac, who developed the relativistic version of quantum mechanics and predicted the existence of antimatter from his equations alone, was asked late in life what he found most significant about quantum mechanics. He said, "The most surprising thing about the quantum theory is that it works." He did not mean that as a joke. He meant that the mathematical framework, developed from a collection of strange postulates and guided by experimental results, produces predictions of extraordinary accuracy, and that the framework is so unlike anything that classical physics suggested, so disconnected from common sense, that the fact that it works is itself astonishing. The universe, at the quantum level, is the way it is, not the way we would have designed it if we were in charge. The double-slit experiment is the clearest demonstration of this. We did not design the universe to be this way. We observed that it is this way. And every time we have tested it, in every possible refinement and extension, it remains this way. The interference pattern appears when no one is watching. It disappears when someone looks. The past is not fully determined until a measurement is made. Information shapes physical outcomes. This is nature, not as we would like it to be, as it actually is. Now I want to spend some time on something that I think gets lost in most explanations of the double-slit experiment, the mathematical structure behind it, not the full formalism, but the key conceptual step that makes sense of the strangeness. The key is the concept of the wave function. In quantum mechanics, every physical system is described by a wave function. The wave function is a mathematical object, a function of position and time, that encodes all the information about the system. The absolute square of the wave function at any point gives the probability of finding the particle at that point if you measure its position. The wave function is not a physical wave. It is not a wave in space the way a water wave is. It is a mathematical object that lives in an abstract space of possibilities. But it obeys a wave equation, the Schrödinger equation, and it exhibits wave-like behavior including interference and diffraction. When an electron approaches the double slit, its wave function spreads across both slits simultaneously. On the other side of the barrier, the parts of the wave function that pass through the left slit and the right slit overlap and interfere. The interference produces a pattern in the wave function, with regions of high probability and regions of low probability. When the electron is finally detected, it lands in one of the high probability regions, randomly selected according to the probabilities encoded in the wave function. Over many trials, the accumulated dots trace out the probability pattern, the interference pattern. Now, you place a detector at one of the slits. The detector interacts with the electron if the electron passes through that slit. This interaction entangles the detector with the electron. The wave function of the combined system now has two branches. In one branch, the detector fired, and the electron went through the left slit. In the other branch, the detector did not fire, and the electron went through the right slit. These two branches are correlated with different, macroscopically distinguishable states of the detector. They cannot interfere. The interference pattern is gone. The electron lands as if it went through one slit or the other, not as if it went through both. This is the mathematics. The wave function tells you everything. When the wave function has two branches that can interfere, you get an interference pattern. When the wave function has two branches correlated with different macroscopic states and cannot interfere, you get two piles. Which you get depends on which way information is encoded in the environment. That is the double-slit experiment, reduced to its mathematical essence. But the mathematics, as elegant as it is, does not dissolve the mystery. It just gives the mystery a precise form. The mystery is, what is the wave function? Is it a real physical thing, spread across space, that actually passes through both slits? Or is it a mathematical tool, a way of encoding our knowledge about the electron, that does not correspond to anything physical in between measurements? If the wave function is real, then the electron really does go through both slits simultaneously. There really is something spread across both paths, not just in our description, but in reality. This view, sometimes called wave function realism or scientism, takes the mathematics seriously as a description of reality. It leads naturally to the many worlds interpretation, where both branches of the wave function are real, and to pilot wave theory, where the wave function guides a particle that really does take one path, but is influenced by a real wave that goes through both. If the wave function is not real, if it is just a mathematical tool for calculating probabilities, then there is nothing physical going through both slits. The electron takes one path, we just do not know which one. The interference pattern arises not from the electron interfering with itself, but from What? This view, associated with Copenhagen and with more modern approaches like cubism, struggles to explain why the mathematics of the wave function is so exquisitely predictive if it does not correspond to anything real. The debate between e-scientism and psi-epistemic views, between treating the wave function as a real physical thing and treating it as a mathematical description of our knowledge, is one of the most active and unresolved debates in the foundations of physics today. And it matters practically, not just philosophically. If the wave function is real, then quantum mechanics may one day need to be completed by specifying what the wave function is, how it relates to physical space, how its branches relate to each other. If the wave function is epistemic, then quantum mechanics may one day be replaced by a deeper theory that explains the probabilities in terms of something more fundamental. Both possibilities are alive. Both are being explored, and the double-slit experiment is the cornerstone of both, because it is the experiment that makes the wave function indispensable. You cannot explain the interference pattern without wave-like behavior, and you cannot explain the disappearance of the interference pattern without the entanglement of the wave function with the measuring device. The wave function is doing essential work in the description. Whether that work is descriptive or ontological is the question. We are living right now in the middle of one of the great unresolved intellectual debates in science, and it all centers on two slits in a wall. Let me close tonight in the way the experiment itself closes, with a dot on a screen. Somewhere, right now, in a laboratory somewhere in the world, an electron is being fired at a double slit. It is traveling through the apparatus. Its wave function is spreading, evolving, dividing at the slits, interfering with itself on the other side. And in a fraction of a second, it will arrive at the detector screen and make a dot. A single, tiny, definite dot. That dot is the universe making up its mind, or the universe crystallizing a potentiality into an actuality, or the universe's wave function branching and you finding yourself in one branch, depending on your interpretation. But the dot is real, and the pattern of 10,000 dots accumulated over 10,000 shots is real. And the interference pattern those dots form, the multiple bright bands, the dark gaps, the signature of something that went through both slits at once, is real. And neither the dot nor the pattern, neither the particle nor the wave, is something that classical physics can explain, something that common sense can accommodate, something that fits into the world as we thought it was. The world is not as we thought it was. The double-slit experiment proved this, definitively, repeatedly, across 2 centuries. And it is still proving it today, in laboratories that Young could not have imagined, with particles that Feynman could not have imagined, and with precision that would have astonished everyone who has ever thought about this experiment. 2 slits, 1 particle, the most disturbing experiment in the history of science, and it is still not finished. I want to spend a little more time with you before we close, because there is something about the double-slit experiment that I have not yet said directly. Something that I think matters more than any of the individual results we have covered. The double-slit experiment does not just tell us something strange about electrons and photons. It tells us something about the relationship between the act of knowing and the nature of what exists. And that relationship is unlike anything we encounter in everyday life, unlike anything classical physics prepared us for, and unlike anything we would have imagined if the experiments had not forced us to face it. In the world of everyday experience, knowing something does not change it. You can look at a rock without changing it. You can measure the temperature of a room without affecting it meaningfully. Knowledge is passive. It receives information from the world, but does not alter the world in return. The world is out there, with its properties. And knowledge is our internal representation of those properties. The map and the territory are separate. The territory does not change because of the map. The double-slit experiment says that, at the quantum level, this is wrong. The particle's behavior, the very physical pattern it creates on the screen, depends on whether information about its path is available, not on whether you personally check the information, not on whether anyone looks, on whether the information is physically encoded in the environment at all. This is a statement about the world, not about us. It is not saying that human minds are powerful enough to change the trajectory of electrons. It is saying something more subtle and more profound. It is saying that the physical world, at the quantum level, does not have a fact of the matter about which slit the particle went through unless and until that fact is recorded in some physical system. The fact does not exist before it is recorded. The recording creates the fact. This is what physicists mean when they talk about measurement creating reality rather than revealing it. Not that we create reality with our minds, but that physical measurement, the irreversible encoding of information in a macroscopic system, is what brings quantum possibilities into definite existence. The implications of this are still being worked out. What does it mean for physics to say that facts do not exist until they are recorded? What is the difference between a fact that exists and a fact that does not? What makes a recording count as a recording? These are questions that the double slit experiment raises and that Quantum Foundation's researchers are actively trying to answer. One approach that has gained significant traction in recent years is called relational quantum mechanics, proposed by Carlo Rovelli in 1996. In relational quantum mechanics, quantum states are not objective features of particles. They are relational. They describe the state of a particle relative to a given observer or measuring device. Different observers can have different, even inconsistent descriptions of the same system, and both descriptions are equally valid from their respective perspectives. In relational quantum mechanics, the double slit experiment has a clean description. Relative to a measuring device placed at the slits, the particle has a definite path. Relative to the final detector screen, with no intervening measurement, the particle has an indefinite path and produces an interference pattern. There is no inconsistency because there is no absolute, observer-independent description of the particle. All descriptions are relative to observers. This view is philosophically radical. It says that there is no view from nowhere, no perspective-independent reality. Every description of reality is always a description relative to something. And the double slit experiment, with its demonstration that the presence or absence of a detector changes the observed outcome, is the clearest experimental support for this view. Whether relational quantum mechanics is the correct interpretation is not settled, but it is a serious, mathematically precise proposal that takes the lesson of the double slit experiment and runs with it as far as it will go. Another recent development is the reconstruction of quantum mechanics from information theoretic principles. Several groups of physicists have shown that quantum mechanics can be derived, not postulated, from a small set of principles about information and probability. These reconstructions suggest that quantum mechanics is not a theory about particles and waves, but a theory about how agents can use information about a physical system to make predictions. In this framework, the double slit experiment looks like this. When no which way information is recorded, the agent has maximal information about the interference between the two paths, and uses that information to predict an interference pattern. When which way information is recorded, the agent has maximal information about the path, but loses all information about the interference. The two kinds of information are complementary. You cannot have both simultaneously. This is Bohr's complementarity principle, rebuilt from information theory. The information theoretic reconstruction suggests that quantum mechanics is the unique theory consistent with certain principles about the relationship between information and probability. In a sense, quantum mechanics is the theory you get if you take information seriously as a fundamental concept, as seriously as energy or momentum. This is a beautiful idea, and it connects the double slit experiment to deep questions in information theory, probability, and the foundations of reasoning. The experiment is not just about particles and slits. It is about what it means to know something, about the relationship between knowledge and reality, about the structure of a world in which information is physical. I have one more thing to say, and then I will truly let you sleep. The double slit experiment is 220 years old. Thomas Young performed the first version in 1801. In the century that followed, it was used to establish the wave nature of light. In the century after that, it revealed wave-particle duality, the uncertainty principle, the measurement problem, and the foundations of quantum mechanics. In the 21st century, it has been performed with molecules of hundreds of atoms, extended into the time domain, connected to questions about quantum gravity, and used to probe the foundations of quantum information theory. It is the same experiment, two slits, one particle, a screen, and yet it has been inexhaustible. Every generation of physicists has found new depth in it. Every refinement has revealed new strangeness. Every attempt to explain it has generated new questions. There is something to learn from this about the nature of scientific understanding. The deepest experiments are not the ones that close questions. They are the ones that keep opening them. The ones that, no matter how carefully you look, always show you something you did not expect to see. The ones that resist final explanation and keep pointing at something deeper. The double slit experiment is the deepest of these. It has been pointing at the mystery at the heart of quantum mechanics for over 200 years. And the mystery is still there, still unresolved, still generating genuine debate among serious physicists who have spent their careers thinking about it. This is not a failure of physics. This is what physics looks like at the frontier, at the place where our understanding ends and the unknown begins, where the experiments are clear and the mathematics works and the interpretations are still being fought over, and the deepest questions are still open. You are living in that moment. Right now, in 2025, the double slit experiment is still generating new results. The debate about what it means is still alive. The measurement problem is unsolved. The interpretation debate is unresolved. The connection to quantum gravity is unknown. The most important experiment in the history of physics is still not finished, and that means the most important questions in physics are still unanswered, still waiting. Still available to the minds that are willing to sit with the discomfort of not knowing, to resist the temptation of easy answers, and to look, again and again, at two slits in a wall and ask what is really happening. Let me give you one final image to carry with you into sleep. Somewhere right now, in a physics laboratory, someone is in a dark room watching a screen. They have been firing particles at a double slit for hours. Each particle arrives as a single dot, random seeming, landing here, landing there, with no obvious pattern. But they have been watching the pattern accumulate. And now, after thousands of shots, the dots have arranged themselves into something unmistakable. Multiple bright bands of dots, dark gaps between them. An interference pattern, the signature of something that went through both slits at once. The person watching knows what this means. They have studied quantum mechanics. They know about the wave function, about superposition, about decoherence and measurement, and the uncertainty principle. They can do the calculations. They know what will happen before they run the experiment. They can predict the exact position and width of every bright band. And yet, watching the pattern emerge, dot by dot, they feel the strangeness of it again, as if for the first time. Because no matter how many times you see it, no matter how well you understand the mathematics, the fact that a single particle, by itself, with no other particle in the apparatus, can produce an interference pattern that only makes sense if it went through both slits simultaneously, this never quite becomes ordinary. This is what physics at the frontier feels like, not the comfortable click of a solved problem, the persistent, irreducible astonishment of a result that is completely confirmed and completely unexplained. That is predicted by the most successful theory in the history of science, and that nobody, not even the people who use that theory every day, can say they truly understand. The dots accumulate. The pattern emerges. The interference bands grow brighter, and the dark gaps grow darker, and the screen fills with the most disturbing picture in the history of science. And the universe keeps its secret. I want to leave you with 3 facts about the double slit experiment that I think deserve to stand alone, without commentary, because they carry their own weight. The first fact: when physicists fire a single photon at the double slit, with both slits open and no detector in place, the photon still produces an interference pattern, one dot at a time. The interference is not between one photon and another. There is only one photon in the apparatus at any moment. The interference is between the photon and itself, a single particle of light going through 2 places at once, arriving as a single dot but carrying the statistical pattern of a wave. The second fact: the double slit experiment has been performed with molecules called phthalocyanine derivatives, molecules that contain more than 800 atoms each. At room temperature, in a real laboratory, these molecules, each one a tiny machine containing hundreds of atoms, go through both slits simultaneously and produce an interference pattern. Objects large enough that you need only a modest microscope to see them individually, obeying the quantum rules of waves. The wave-particle duality does not stop at electrons. It extends, at least so far, to objects of this size. The third fact. Every attempt ever made to catch a particle going through both slits at once to observe the superposition directly has failed. Not because the attempts were poorly designed, because the act of observing, the act of creating a macroscopic record, always destroys what was being looked for. The superposition is real. The wave passes through both slits, but it cannot be directly observed in the act of doing so. You can only see its consequences in the interference pattern, never the thing itself. The quantum world is, in this precise sense, necessarily hidden. Not hidden from us because we are not clever enough. Hidden in principle. Hidden by the structure of physics itself. These three facts, taken together, describe a world that is both the most familiar and the most alien place in science. A world built from the same matter you are made of, governed by rules that have been confirmed to extraordinary precision, producing phenomena that no human intuition can fully accommodate. This is the double-slit experiment. This is what it shows. This is what physics has confirmed across 2 centuries and thousands of experiments cannot be otherwise. The dots accumulate, the pattern emerges, the interference bands glow on the screen, and somewhere in that pattern, something is pointing at a truth about the universe that we are still slowly learning to read. Physics began with people staring at the sky and asking why things moved the way they did. It has always been, at its core, the practice of asking simple questions about obvious phenomena and following the answers wherever they lead, however uncomfortable the destination. Thomas Young asked a simple question about light. He built a simple apparatus to answer it. And the answer led, over 2 centuries, to quantum mechanics, to the uncertainty principle, to entanglement, to quantum computing, to questions about the nature of reality, observation, information, and consciousness that philosophers and physicists are still actively arguing about today. This is what science is at its best. Not the triumphant announcement of final answers. The humble, persistent, endlessly generative practice of asking the next question. Of looking again. Of not being satisfied with an explanation that does not quite explain. The double-slit experiment is 220 years old. It is more productive today than it has ever been. More refined, more extended, more deeply connected to the central questions of physics than Thomas Young could have imagined. That is the experiment. That is the mystery. That is the invitation. We began tonight with a promise. We said we were going to look at one experiment, one simple apparatus, a wall, 2 slits, a particle gun, a screen. And we said that what happens when you run it is so deeply disturbing that Richard Feynman called it the only mystery of quantum mechanics. We have kept that promise. We have seen exactly what happens. We have traced the history from Young to Bohr to Heisenberg to Feynman to Bell to the present day. We have followed the experiment into the delayed choice, the quantum eraser, the temporal double slit, the experiments with molecules of hundreds of atoms. We have explored the interpretations that physicists have proposed to make sense of the result and found that none of them is fully satisfying. We have seen that the strangeness is not going away, that every deeper look reveals a deeper mystery, that the most successful theory in the history of science is also the least understood. 2 slits, 1 particle, 220 years of science, and still pointing at something we cannot quite see. That is where we are. That is the edge. And if the edge makes you uncomfortable, that is exactly the right response. It should. The universe at its most fundamental is not comfortable. It is extraordinary. One last thought. The double-slit experiment, in all its forms, all its refinements, all its disturbing implications, has one thing that it cannot tell you. It cannot tell you what to do with the knowledge, what it means for how you live, how you see the world, how you relate to other people and to the universe around you. That is not physics. That is yours. Physics gives you the facts. What you make of them is entirely up to you. But knowing the facts changes something. Knowing that the world at its deepest level does not consist of solid, separate, definite things. That observation participates in reality. That information is physical. That the universe, at the scale of its building blocks, is strange beyond anything common sense prepares you for. This knowledge does something to a person who holds it honestly. It instills a kind of humility. A recognition that the world is larger and stranger than any single framework can contain. A willingness to sit with mystery rather than rushing to dissolve it. The double slit experiment has been teaching this lesson for 220 years, and it is still teaching it tonight. Good night.